We have been learning about the limit of a polynomial or a rational function as x approaches a for the past few lessons, and where we know that this a is any real number. Now in this lesson we will learn to determine the limit of a function as x approaches infinity, or the limit of a function as x approaches negative infinity, if it exists. And it's important to learn these limits because they tell us the behavior of a function at far right and at far left of the graph of a function. So let's see how. So I'm going to start with the polynomial functions. So consider a polynomial function defined as x cubed minus x. And let's say we have to determine the limit of x cubed minus x as x approaches infinity. It's important to note that we cannot determine this limit by applying the limit law. That is, we cannot write this limit as limit of x cubed as x approaches infinity minus limit of x as x approaches infinity. Because as x becomes large, obviously x cubed becomes larger than x. So it's reasonable to say that as x approaches infinity, x cubed approaches infinity as well. So this limit is infinity. And this limit is obvious again because here the function is x itself. So as x approaches infinity, this function x approaches infinity. So this limit is also infinity. So we have minus infinity. Now when we see infinity minus infinity, we are tempted to write it as 0. But all these steps right here are absurd. I should not have written it like this. Because infinity minus infinity can't be defined. And the reason is obvious. As we learnt in our past lessons that infinity cannot be treated like a number. It's something which is larger than any number. And roughly speaking, it continues to grow without any bound. It is endless. So we cannot locate this infinity on our coordinate axis. So we cannot take this as some fixed thing minus the same fixed thing to get 0. No, we cannot do it. So because of the endless nature of infinity, this infinity minus infinity can't be defined. So we have that infinity minus infinity is undefined. So we have to take another approach to see if this limit exists or not. So what we are going to do here is that we are going to compare the rates of x cubed and x at which they become large as x become large. So for that, I'm going to show you the graph of x cubed and x on the same coordinate axis, and which I have right here. You can see here that the graph in the color blue is x cubed and the graph of the function x is right here. Although in order to determine this limit as x approaches infinity, we are only interested in large values of x. But just to get an intuition, for instance, let's consider x is equal to 10. So we can see that when x is equal to 10, this function x becomes large just by 10 units. Whereas the function x cubed becomes large by 1000 units at x is equal to 10. So as x increases, x cubed continues to become larger and larger much faster than x. So it's reasonable to say that as x approaches infinity, x cubed becomes large as compared to x, so much so that it dominates and x loses its effect. So which means that the behavior of this function as x approaches infinity is similar to the behavior of x cubed as x approaches infinity. So that's why we write this limit as limit of x cubed as x approaches infinity. So what I have done here, in order to determine this limit, I have retained the highest power term from this expression because it dominates, and I ignored the lowest power term because its growth does not count as compared to the growth of x cubed when x approaches infinity. So finally, we write this limit as infinity. So in general, the limit of Any polynomial function as x approaches infinity is determined by its highest power term because it dominates as x approaches infinity, and we can neglect all the lower power terms because their growth doesn't count as compared to the highest power term when x approaches infinity. And this limit is called infinite limit at infinity. And we can use the same approach even if a function is not a polynomial. So let's quickly look at a function which is not a polynomial. Suppose I have a function defined as e to the power of x minus 7 to the power of x. And let's say we have to determine the limit of e to the power of x minus 7 to the power of x as x approaches infinity. Again, we see that for large x, e to the power of x is even larger. So as x approaches infinity, e to the power of x approaches infinity as well. And the same is true for 7 to the power of x. So again, this is the case of infinity minus infinity, and which can't be defined. So in order to determine this limit, let's compare the rates at which these two functions become large as x becomes large. So for that, again, I'm going to show you the graph of e to the power of x and 7 to the power of x on the same coordinate axis, and which I have right here. You can see that the graph of 7 to the power of x is in the color blue, and this is the graph of e to the power of x. So for instance, let's consider x is equal to 5. So at x is equal to 5, we see that e to the power of x becomes large just by about 148 units. Whereas at x is equal to 5, this function 7 to the power of x, it becomes large by more than 16,000 units. So as x increases, 7 to the power of x continues to become larger and larger, much faster as compared to e to the power of x. So obviously, as x approaches infinity, this 7 to the power of x becomes large as compared to e to the power of x, so much so that it dominates. And e to the power of x loses its effect. So in this case, as x approaches infinity, the behavior of this function is same as the behavior of 7 to the power of x, but in the negative y direction. So in order to determine this limit, what we'll do is that we'll retain the term 7 to the power of x and we'll ignore e to the power of x. So we will write this limit as limit of minus 7 to the power of x as x approaches infinity, and which obviously is negative infinity. So as x approaches infinity, the behavior of this function e to the power of x minus 7 to the power of x is same as the behavior of the function minus 7 to the power of x, and which you can see graphically as well. Here you can see that the graph of e to the power of x minus 7 to the power of x progresses in the negative y direction, and it approaches negative infinity as x approaches infinity. Now, in our next lesson, we will learn to determine the limit of a rational function as x approaches infinity, and there we will make use of what we learned in this lesson.